Good afternoon, everyone. We are Group 25, composed by Aiden Hayes, Emily Waltz, me, Rebecca Silhi, Brandon Snyder, and Amir Maksutov. Today, we will be presenting our project on orbital mechanics, focusing specifically on the Hohmann transfer. Our objective for this project was to apply Newtonian and Keplerian mechanics to understand satellite motion. We specifically focused on deriving the key equations related to Hohmann transfers, simulating orbital motion using MATLAB, and connecting theoretical results to real world satellite operations like orbital transfers and mission planning. What is a Hohmann transfer? A Hohmann transfer is an energy efficient maneuver used to move a satellite between two circular orbits. It requires two main engine burns, one to move the satellite into an elliptical transfer orbit, and another to circularize it at the new altitude. This method minimizes the total amount of energy required for the transfer, making it very useful for mission efficiency. However, it assumes that both orbits are circular and coplanar, meaning they are in the same plane. The Hohmann transfer remains one of the simplest and most widely used techniques for changing orbital altitudes.
Why do Hohmann transfers matter? First and foremost, they dramatically improve fuel efficiency. By minimizing the total energy required, we can save precious fuel compared to direct transfers. This efficiency makes them ideal for two critical operations: initial orbit insertion when launching satellites, and later repositioning those satellites as needed. However, their importance goes beyond just saving fuel. These transfers provide the foundational concepts for all trajectory planning. If we're timing a resupply mission to the International Space Station, the principles behind the Hohmann transfer can ensure precise orbital dockings. What are the key assumptions that we made? We modeled the Earth and the satellite as point masses, a valid approach because their physical sizes are negligible compared to the orbital distances. We assumed Earth is perfectly spherical, which is nearly true for most practical purposes, and we neglected atmospheric drag since its effects are minimal above 200 kilometers altitude. Our analysis also focuses exclusively on the two-body problem, meaning we only consider gravitational interaction between Earth and the satellite, ignoring other celestial bodies. Finally, we treat the satellite as a rigid body, assuming no structural flexing or rotational effects that might alter its trajectory. While these assumptions don't capture every real-world complexity, they provide an excellent starting point that can be refined as needed.
Let's walk through the math behind the Hohmann transfer. We simplify our free body diagram to only consider the effects of gravity and disregard any potential atmospheric drag. For an object to remain in orbit, its centripetal force and gravitational forces must be equal. From this, we can find our first formula, the velocity of an object in orbit. Next, we use the concept of mechanical energy to understand the changes during the transfer. Our mechanical energy remains constant for any point in this orbit, so we can set total energy equal to negative g times the mass of the planet multiplied by the mass of the satellite over 2r. When we shift to an elliptical orbit after the first burn, we replace r with a, the semi-major axis, which is found by taking half of the radii of our current and desired orbits added together. This gives us the mechanical energy of an object in elliptical orbit. We can now plug in our elliptical mechanical energy formula, which gives us a new total energy formula and lets us solve for the satellite's velocity right after the burn using what's known as the Vis-Viva equation. This equation can be used to find velocity required for the Hohmann transfer after each of the two burns. This change in velocity is crucial information as it allows use of the impulse momentum theorem that can determine the amount of fuel needed for this maneuver. For further analysis, we can use Kepler's laws to find the time it takes for our satellite to complete this transfer. The transfer sweeps a path that is half the total elliptical path, so the time our satellite takes would be half of Kepler's third law.
This slide shows our MATLAB simulation of the Hohmann transfer. We did include some of the code that we did use in MATLAB, including the velocity formulas as well as the time period formulas that we used and derived in order to create this Hohmann transfer representation on MATLAB. The Hohmann transfer is a fuel-efficient way to move a spacecraft between two orbits, and it does have direct relevance to numerous space missions as well as commercial ventures, such as satellite constellation deployment, which is used by companies like SpaceX. It also is used in orbital and docking missions, as well as geostationary orbit insertions and the installation of satellites around other planets, which, for example, this could be used for probes to Mars or Jupiter, and you would use the Hohmann transfer to enter the orbits around other planets with low energy costs, because this is a low energy and fuel efficient way to orbit other planets.
In this example from our report, we used the Hohmann transfer analysis in order to find the transfer velocities as well as the total time necessary to move a satellite from orbit from 6,000 kilometers around the center of the Earth to 10,000 kilometers around the center of the Earth. Now, a few limitations applied to the Hohmann transfer that we haven't covered in our derivations or in our example. In our models, we assume that the Earth and the satellite are the only two bodies in the system, but this isn't true in real life. There's the moon, there's the sun, there's all sorts of other celestial bodies that can impact a satellite's orbit. Along with this, we haven't taken into account any potential atmospheric drag. We haven't taken into account the Earth's shape, which can impact orbit. And we haven't taken into account the fact that real thrusters take time to apply thrust to the satellite. And so it wouldn't necessarily be an instantaneous change in velocity as we see in our derivations. In conclusion, the Hohmann transfer is an important aspect of orbital mechanics that we use for many, many different satellites orbiting the Earth. It is the most efficient two-impulse method of transitioning from one orbit to another, although many of the assumptions made during the derivation of the Hohmann transfer may not stand in real space applications due to external celestial bodies.